2 is scheduled for this Thursday. And exam 2 is open book and open notes. So although exam 2 is open book and open notes, it doesn't mean that you don't want to study for the exam. So you also don't really want to spend time flipping through your notes or the textbook trying to find an answer to a question, because it's probably not going to be in your textbook. So the questions and problems on the exam will involve solving problems. So I hope you'll be able to show me that you can apply the principles and theories and laws that we've looked at since exam 1 on exam 2. I'll also bring a calculator to the exam. Also on Friday at UC Santa Cruz, the Access program is holding their spring lab tour. That goes from 3 to 6. And there will be tours of the Nuclear Magnetic Resonance Facility at UC Santa Cruz, as well as 2 labs. Professor Karen Ottoman and Professor Ted Holmer will give a talk on their research and also give a tour of their labs. So I encourage all of you who are interested in either attending UC Santa Cruz or doing one of these summer research internships to attend this lab tour. And then Pam Darcy, who is the co-director of the Access program, told me to tell you that they'll be serving fresh baked pizza as their refreshments during the spring lab tour. Okay, so pass back the quiz. Should we review the quiz before moving on? No? No? Okay, so based on that response, I guess we're going to move on.
Oh, I said no.
Huh?
Let's move on. Let's go over it. Let's go over it. Yeah, we got it.
Okay, so for question 1A, how would you calculate delta H for this reaction? What equation or formula would you use? Yeah, so for question 1A, what formula would you use? Yeah, Hess's law. So where in the textbook would you use the information and apply Hess's law? Appendix 2. So remember that for Hess's law, it's the sum of the heats of formations of the products minus reactants, and you also have to multiply by the coefficient in the balanced chemical equation. For question B, how do you determine whether a reaction produces work? Not delta S. Delta what?
Delta N.
Yeah, delta N, so what's N? Yeah, so note that it refers to gases. So note that in this equation here, there's only 2 gases out of 3 substances. So there's 2 gases producing products. Note that the H2O is a liquid, so you don't refer to the H2O liquid now. So again, if delta N is less than 0, what is work? Greater than 0 or less than 0? So delta N is less than 0, that means work is going to be greater than 0. Okay. How do you determine whether a reaction occurs spontaneously? Yeah, so look, now how do you calculate delta G? What formula do you use? Okay, again, use Hess's law. Look up the delta G of formation in Appendix 2, then for Part D. If the reaction is not spontaneous, is there a temperature? How would you answer the question D? What formula would you use there? Yeah, so use that formula that Rolando just described. So in Part A, you calculated delta H. How do you figure out delta S? Yeah, use Hess's law again. And then to figure out the temperature, you set delta G equal to 0. Okay, so you have 0 equals delta H minus T delta is solved for T. For question 2, what is the function of the fuel in a heat engine? So in a heat engine, we've looked at that schematic diagram. Okay, so there's our hot reservoir. Here's our cold reservoir. So the fuel is doing something in the hot reservoir. So what's the fuel doing? Yeah, so notice that the fuel in the hot reservoir produces heat. And then once this heat is produced, part of this heat is converted into work. Okay, so it turns out that the fuel is actually used to produce heat, and then that heat is converted into work. Okay, so it's not really that the fuel is used to produce work, because some fuels won't produce work. The efficiency is work divided by QH. Why does an engine have such a low efficiency? And if we look at those thermodynamic quantities, what thermodynamic quantity are you looking at in Part B? Delta S. So is delta S greater than 0 or less than 0 in a heat engine? In other words, what does delta S tell you about the efficiency of the heat engine? Okay, delta S is greater than 0, and if we look at another diagram of a heat engine, okay, so this is the cylinder in an engine. So we have the combustion reaction going on inside the cylinder. So what is delta S telling us? That the gases are moving in different directions. They're not all moving in the same direction. So if you can get all these gas molecules to move in the same direction, push that piston, that means engine work will be involved. It can't be that. And then Part C, what happens to the refrigerant to cool air inside a refrigerator? So rather than writing that diagram on the chalkboard. Okay, so in which step is the air being cooled inside the refrigerator? A, B, C, or D? Which one? Are you guys saying B? D? Okay, so it should be D. So note that in D, a liquid is converted to a gas. And in this evaporation step, delta H is less than 0 or greater than 0. So when a liquid is converted to a gas, when a liquid vaporizes, delta H greater than 0 or less than 0? A greater than 0. So where is the heat coming from to vaporize the liquid? Yeah, so that heat is coming from inside the refrigerator compartment. In other words, the air inside the refrigerator is losing heat. The refrigerant liquid is gaining heat, and in that step, that's what cools the air inside the refrigerator. Okay, are there any other questions on quiz 11? Okay, so let's see. Let's go over this question. So the 3 laws of thermodynamics are: energy is neither created nor destroyed. What equation represents the first law of thermodynamics? So for the first law, that equation is represented by Well, that's part of the equation. Note that in the equation you have something equals something else. Equals what? What's thermal energy? Yes, you're close, but it's actually delta E, which is the internal energy, equals Q plus W. Okay, so delta E, this is the change in internal energy. So what this tells us is that the energy inside atoms and molecules can be converted into either heat or work or both. The second law states that the total energy in the universe is increasing. So what does that tell us about delta S in the universe? Is it greater than 0 or less than 0? Yeah, so for the second law, delta S in the universe is increasing. So if this is the case, is the universe expanding or is it contracting?
Expanding.
And if you've taken astronomy, what observation tells you that the universe is expanding? Yeah. So what is it called? Is it called a red shift or a blue shift? Red shift versus a blue shift. So which one is it? Tell us that the universe is expanding? Red or blue? It's red. It's a red shift. So note that in the red shift, what's it's doing is that if you have, if this is a wave, and if the universe is expanding, note that the wavelength is actually getting longer. So that represents the longer wavelength, which is going toward the red. So I'm not sure if that corresponds or correlates with the increasing waistline of us Americans. So we need to watch our health. And for the third law, a substance at 0 degrees Kelvin has an entropy of 0. Rolando.
So then, delta S is increasing because since it's accelerating.
Yeah. That's what the guy got the Nobel Prize for, right? The galaxies are constantly increasing and accelerating.
Yeah, some guy, I can't remember. Yeah. Yeah, because really, see, the form of this one is that the delta S of the surroundings, delta S of the universe is equal to what they say delta S of the system, which you're studying, plus the delta S of the surroundings. So for example, if you're looking at a chemical reaction or a physical process in which delta S is less than 0, that means that delta S of the surroundings must be greater than 0 because delta S of the universe should be increasing. Okay, for the third law, a substance at 0 degrees Kelvin has an entropy of 0. So what does this mean in terms of reaching absolute 0 as a temperature?
Not possible.
Yeah, not possible. So I think it was almost 20 years ago when researchers at the University of Colorado and the National Institute of Standards and Technology got the world record at that time of the lowest temperature actually measured. That was 190. It was 190 nanokelvin, which is 190 times 10 to the minus 9 Kelvin. This is when they discovered this new state of matter, the Bose-Einstein condensate. And then at that time, I was reading stories in which physicists were thinking that, well, heck, we can reach absolute 0, and not only that, we can reach temperatures below absolute 0. Which, if that was the case, then you're going to have to rewrite the laws of at least that third law of thermodynamics. So I don't think that's happened yet. But anyway, at that time, scientists think about that. Okay, let's take a look at these restatements of the 3 laws of thermodynamics. You can't win, you can't break even, you can't quit. So which statement corresponds to which law of thermodynamics? So what I'd like you to do for the next minute, since I think we probably want to spend some time reviewing some questions for the exam. So take a minute, and which statement corresponds to which law of thermodynamics? So it's one statement per law.
But I can't win.